It is known that tornadoes occasionally contain flying debris, but there is no evidence that heavy debris can be picked up and driven great distances at high velocities by tornado winds. Nevertheless, nuclear facilities are designed under federal regulations to withstand highly unlikely impacts from such debris. This film describes a test program to demonstrate the protection provided by nuclear power plant walls against such hypothetical impact. This was Sandia Laboratories for the Electric Power Research Institute in cooperation with the U.S. Energy Research and Development Administration. Reactor containment buildings have reinforced concrete walls from 3 to 5 feet thick. These are more than adequate for protection against even the most severe tornado debris, as may be gauged by this cross-section of a reactor containment wall under construction. It is rather the thinner concrete walls protecting safety-related equipment in auxiliary buildings that were simulated for study in this test program. Full-scale tests simulating impact by tornado-driven debris were carried out at Sandia's Tonopah test range on the desert of central Nevada. Here, concrete test panels were specially built to represent nuclear plant walls and roofs, and a rocket sled track constructed to launch simulated tornado-driven missiles against them at high speed. A full-scale test looked like this. A slow-motion film of the same test more clearly shows a missile traveling in free flight and striking the test panel. 4 types of missiles were used in the tests: a 15-foot length of large diameter pipe, a 35-foot utility pole, a 10-foot long section of small diameter pipe, and a 3-foot piece of steel reinforcing bar. These were postulated for design purposes to be potential projectiles in the vicinity of a nuclear power plant. Impact velocities in the tests spanned a range from 60 to 200 miles an hour. They included velocities corresponding to assumed tornado wind speeds as high as 360 miles an hour. This is conservatively high and contrasts with maximum tornado wind speeds of 175 to 225 miles an hour, recently cited by the National Severe Storms Laboratory. To control test velocities and the point of impact, an I-beam was used as a rocket sled track with a cage surrounding the top rail to guide the missile. Riding on non-gripping shoes, the missile was positioned on the track. And the rocket sled drawn up behind it. Velocities were predetermined by the number of rocket motors used to propel the sled and by the distance the missile was driven by the sled. At the end of the track, the sled was stopped by a honeycomb energy-absorbing structure, thus launching the missile in free flight. 17-foot square target panels of reinforced concrete were fabricated at the test range in 3 thicknesses: 12, 18, and 24 inches. The target panels were specially built to meet standards of the U.S. Nuclear Regulatory Commission. The concrete strength after curing measured about 3,600 pounds per square inch. The panels contained a minimum allowable reinforcing steel at each face and had no shear reinforcement. The completed panels were lifted into place against a specially designed support structure. At the front end of the support structure was a 3-foot deep, 1-foot wide square reinforced concrete reaction beam. This beam provided a 15-foot square unsupported span for the test panel and transmitted loads to the load cells, which were positioned at each corner between the reaction beam and the backup structure. The load cells recorded the total reaction force history produced by missile impact. Behind the reaction beam was a 1-foot thick backup structure that reacted impact loads by means of both its mass, some 40 tons, and footings that transmitted forces to the ground. Test instrumentation included 6 high-speed cameras to view missile flight and panel damage during impact, 6 velocity transducers to record the motion imparted to the back face of the test panel by the impacting missile, and 3 strain gauges welded to the reinforcing bars to measure strain during impact. 2 tests in the program used 35-foot pine utility poles that were 13 inches in diameter and weighed about 920 pounds. The weight was increased to the specified design weight of 1,500 pounds by attaching a 10-foot length of 12-inch pipe to the back end of each pole. In the first of the 2 pole tests, the impact velocity was 204 feet per second, or about 140 miles per hour. The pole splintered heavily, the first 4 feet disintegrating as it struck an 18-inch thick panel. But the face of the panel was undamaged, and only hairline cracks appeared on the panel's back face. The second pole, traveling at the same velocity, struck a thinner panel 12 inches thick. Again, the pole splintered and produced minor cracks in the wall's back face, demonstrating the wall's ability to protect a power plant during a tornado. In other tests, 8-pound sections of reinforcing bar were driven into test panels. A head-on impact at 200 miles per hour had virtually no effect on the front end of the rebar. The steel bar penetrated some 3½ inches into the front surface of the 18-inch wall, but the panel's back face was completely undamaged. A 3-inch pipe weighing 78 pounds struck a 12-inch wall at 140 miles per hour. This resulted in a 4½ inch penetration into the panel's front face and only hairline cracks on the back face. Unlike the rebar, the pipe dissipated energy as its impact end deformed appreciably. The final type of missile tested was a larger pipe, 12 inches in diameter, weighing almost 750 pounds. At 140 miles an hour, the pipe penetrated partially into a 24-inch panel, but produced only hairline cracks on the back face. At the same velocity, another 12-inch pipe penetrated a thinner 18-inch panel to the same depth, but pieces of concrete scabbed from the back face. This test shows that such damage is caused only by missile velocities greater than those being considered as worst-case design conditions. These, in turn, are based on maximum tornado wind speeds about twice those estimated by the National Severe Storms Laboratory. The front ends of the pipe deform severely, absorbing energy. A third 12-inch pipe, striking an identical panel, but at a lower velocity of 100 miles an hour, penetrated to a lesser depth and produced cracks on the back face, but virtually no scabbing. This is an important finding because this test velocity is the one presently being considered as the worst-case design condition. In all tests seen previously, the worst case of a direct right-angle strike was assumed. In an actual situation, a random oblique strike would be much more likely to occur. To demonstrate that oblique strikes cause less damage, a 12-inch pipe was launched with the rocket track inclined 45 degrees to an 18-inch panel. In this direct front view, a protective barrier is at the right and the end of the track is at the left. As you will see when the dust clears, the 140 mile per hour impact produced 4-inch deep surface damage to the wall. But the back face had only hairline cracks and not the scabbing caused by the right angle test at the same velocity. A slow-motion view of the oblique test was filmed from above by a camera suspended from a crane. As it turned out, the barrier was not needed. The pipe ricocheted and fell harmlessly to the ground. The impacted side of the pipe was severely deformed. In summary, the tests indicated that nuclear facilities are structurally safe, even if struck by heavy tornado debris driven to improbably high speeds. 3 out of 4 types of potential projectiles were ineffective in damaging concrete walls, even though the unlikely worst case of a direct right-angle strike was assumed. In the 4th case, it was demonstrated that a 24-inch thick wall provides ample protection against impact from a heavy steel pipe traveling at 140 miles an hour. An 18-inch wall provides similar protection against a 100-mile-an-hour strike. The test program was heavily weighted on the conservative side of safety. Maximum test velocities were well beyond the range of any ever expected to occur. Design basis velocities are expected to decrease as we learn more about maximum tornado wind speeds and about realistic aerodynamic behavior of tumbling debris. In one instance where a tornado passed directly over a utility storage yard in Kentucky in 1974, utility poles stored on racks were merely dislodged and thrown to the ground nearby, but did not become airborne. Thus, a fundamental question still exists as to whether such heavy objects could even become airborne at all. These issues are being studied in separate but complementary projects sponsored by the EPRI, ERDA, and NRC. Detailed measurements and technical results of the test program appear in this EPRI report, which is available upon request. Copies of this film may also be obtained for showing from EPRI.
Safe design of nuclear power plants requires consideration of their resistance to impact by accidentally produced flying objects referred to as missiles. This film reports research on the containment of such missiles. In earlier research on tornado missile effects, full-scale rocket sled tests like this demonstrated that reinforced concrete walls and roofs are completely adequate to protect safety-related plant equipment against impact of steel pipes or wooden poles that might become airborne in a tornado. Experimental efforts have shifted to study the containment of missiles, which hypothetically could be produced by the failure of a rotating part of a large steam turbine. The failure considered in nuclear plant design is the fracture of the steel disc that holds the rotating blades. For licensing purposes, it has been calculated that the probability of a missile coming through a casing like this one and then striking a safety-related area of the plant is extremely low. To provide data in support of these low-risk estimates, the Electric Power Research Institute sponsored the rocket sled test described in this film. The most energetic fragments would originate from a possible failure in the low-pressure sections of a turbine. It is hypothesized that a disk rotating at more than its 1800 RPM operating speed breaks up into 2, 3, or 4 fragments. As the fragments travel outward, the turbine blades are crushed. Fragments traveling downward would be stopped by the solid reinforced concrete turbine pedestal. The 1 or 2 fragments that might travel upward or outward would strike the heavy steel rings supporting the stator blades and then the lighter steel casing surrounding the turbine. Depending on specific conditions, the fragments would either be contained within the casing or would be slowed down should they penetrate the casing as missiles. The turbine in nuclear power plants is often arranged in such a way that in the event any fragments came through the casing, most would be thrown away from major plant buildings. Other plants have a different layout in which some trajectories of potential missiles intersect the reactor containment or other plant buildings. These buildings are protected by reinforced concrete walls and roofs that are 2 to 6 feet thick. The tests described in this film examine the conditions under which turbine missiles might be contained within the casing or manage to leave it. Subsequent tests will evaluate the effects of those missiles that happen to strike concrete barriers. To provide data for making realistic assessments of turbine missile effects, 2 full-scale tests were performed at Sandia Laboratories' rocket sled facility in Albuquerque, New Mexico. The target structures were simplified representations of a turbine casing and consisted of a thick inner steel ring which simulated the stationary blade ring, and a thin outer steel shell which simulated the outer casing. The ring was 5 inches thick and 15 feet in diameter, while the shell was 1 1/4 inches thick and 20 feet in diameter. These semicircular structures, fabricated from A515 cold-rolled mild steel, simulated the 2 main turbine components expected to absorb the energy of turbine missiles. The ring and shell were bolted at each end by attachments that simulated the horizontal joints in an actual turbine. The target was supported by a massive 1,800-ton backup structure consisting of a thick reinforced concrete foundation covered by a soil overburden. The target and backup structure were situated at one end of a 2,000-foot-long rocket sled track. The reinforced concrete backup structure was designed and constructed to resist the large forces of the impacts. The structural deformation of various points on the ring and shell produced by missile impact was measured by electronic strain gauges. The missile was selected from among spare turbine disc segments contributed by the Westinghouse Corporation and the General Electric Company. The missile selected was a 120-degree segment from a Westinghouse turbine's last stage disc. The 3,400-pound missile was mounted on a carriage sled with explosive bolts. A separate rocket sled pushed the carriage sled and missile down the track. In the 2 full-scale test simulations, the disc fragments had no blades and did not rotate as they left the sled track to strike the target structure. Because the actual impact orientation in a turbine failure cannot be predicted with certainty, the missiles in the 2 tests were given extreme orientations to examine the effects of these orientations on energy absorption. In one test, a piercing orientation with sharp corner impact resulted in less absorption of the missile's energy. Whereas in the other test, a blunt orientation with curved edge impact resulted in greater absorption of the missile's energy. The first test was run with the missile in the piercing orientation. In real time, the test looked like this. High-speed photography was used extensively to slow the action and examine the details of the tests. A rocket pusher sled accelerated the missile. Water brakes were then engaged to stop the pusher sled, allowing the missile carriage to glide to the end of the track. Near the end of the track, the explosive bolts were triggered to separate the missile from the carriage sled. The missile then flew freely to strike the structure at 480 feet per second, representing a hypothetical failure of a nuclear plant turbine spinning 20% faster than its normal operating speed. After separation of the missile, the carriage sled was intercepted by a massive plate, which deflected it downward and away from the target structure. A view from behind the target structure shows the missile being slowed to 60% of its initial speed as it penetrates both the inner ring and outer shell. As the missile leaves the simulated casing, its initial speed of 480 feet per second has been decreased to 285 feet per second. 2/3 of its energy was absorbed by the impact. An overhead view shows the missile fracturing the ring at the impact point. The moving pieces of the ring then break at their gusset plate connection. A close-up shows the missile's sharp edge penetrating about 4 inches into the 5-inch thick ring before the ring fractures 2 milliseconds after impact. Analysis of these close-up movie frames shows that 85% of the total absorbed energy was absorbed before the ring fractured. Perforation of the outer shell dissipates the other 15%. The bent and fractured structure and the indentation produced by the impact indicate how a portion of the missile's energy was dissipated. For the second test, the missile was turned 90 degrees on its carriage so that it would strike blunt edge first, again at 480 feet per second. In this test, the missile did not perforate either the ring or the shell. Instead, the momentum of the impact pulled the end bolts out of their supports. The impact absorbed almost all of the missile's energy. Here, the missile is seen falling to the ground. The overhead view shows the severe distortion of the ring and shell as the end bolts fail. 99.7% of the missile's energy was absorbed by the two structures, slowing it from 480 to 25 feet per second. A close-up shows the ring remaining intact as it conforms to the curvature of the missile. The severely distorted ring and shell attest to the substantial energy absorbed. The high-speed photography in both tests measured missile velocity before, during, and after impact. Strain gauge records show deformation histories on the structures. Detailed data appear in an EPRI final report. The results of these full-scale tests demonstrate that turbine casings can absorb 2/3 or more of initial energy in slowing down or containing the largest fragments from a postulated turbine failure. The full-scale data are being used to validate computer analyses of the impact process. These data and analyses, supplemented with additional full and scale model testing, can be used both for assessing the conservatism in present estimates of turbine missile velocities and for improving design methods. Based upon data developed in this program, a similar approach is currently being followed in turbine missile tests of concrete structures which protect safety-related areas in nuclear power plants.